get started. Hello and welcome to today's edition to NUEPIC's LUS Corrective Action webinar series. Before we get started, I'd like to go over a few items so that you know how to participate in today's event. We've taken a screenshot of an example of the attendee interface. You should see something that looks like this on your own computer desktop in the upper right corner. You're listening using the computer speaker system by default. If you prefer to join over the phone, select the telephone in the audio pane and the dial-in information will be displayed. You will have the opportunity to submit text questions to today's presenters by typing in your questions into the questions pane of the control panel. You may send your question in at any time during the presentation. We will have short Q&A sessions after each speaker's section, as well as a longer Q&A at the end of our webinar as time allows. Please address all questions to a specific presenter by typing their name into the question box. Today's webinar will be on lessons learned from high-resolution site characterization used at leaking underground storage tank sites. My name is Nick Bissonette, and I will be moderating today's session. Drew Youngs from NUEPIC will also be assisting in today's effort. NUEPIC collaborates with and serves state and tribal tanks programs to provide information exchange and training to environmental professionals. For more than 30 years, NUEPIC, in partnership with EPA, has taken a lead role in working with state, tribal, territorial, and federal regulators to reduce the number of underground storage tank releases and minimize the impact of leaking underground storage tanks to the environment and public health. The webinar series, along with LUSline and the National Tanks Conference, are a few of the ways that NUEPIC provides engagement and information exchange for the tanks community to be as well informed and connected as possible. In the handout section of the GoToWebinar panel, you will find a copy of all of the slides for today's presentation. After the completion of today's webinar, you'll be asked to fill out a brief survey. Please take the time to quickly respond and let NUEPIC know how your experience was today. An electronic certification of attendance will be emailed to the address used to register for this webinar. Please note that today's presentation has not been evaluated to meet any continuing education requirements. Now, I'd like to introduce our speakers. John Sohl, the co-founder of Columbia Technologies. John brings to his role of president and CEO 35 years of experience directing the development and innovation of business solutions using science and technology to advance the state of environmental services. At Columbia, John is responsible for overall direction of corporate activities, the quality of the company's field services, and business development. A former officer of the U.S. Navy Nuclear Submarine Force, John holds a BS in engineering from the U.S. Naval Academy and an MBA from Chaminade University in Honolulu. John is a member of the Small Environmental Business Action Coalition, Sustainable Remediation Forum, the Society of American Military Engineers, and the National Groundwater Academy. Dorothy Malaier is a professional geologist who supervises and works with a team of Alabama DEM geologists who regulate the investigation of cleanup of UST releases in Alabama. Working with members of for over 32 years, they have successfully overseen the closure of 93% of all reported releases. Every day is a new opportunity to utilize the existing knowledge and experience to seek new solutions to site challenges. And we also have Ashleigh Thrash. Ashleigh Thrash has been with the South Carolina Department of Health and Environmental Control, DHEC, since 2013. She has experience working in CERCLA and UST programs. She has a bachelor's degree from Clemson University in geology and is a licensed professional geologist in the state of South Carolina. Currently, Ashleigh manages the assessment and non-permitted petroleum section of the UST Management Division of DHEC. And now just a quick agenda. First, we're going to have John going over lessons learned from 150 HRSC investigations and failed UST remediation sites, followed by Dorothy with the high-resolution site characterization in Alabama, a strategy to advance UST release cleanups in Alabama. And we will also have Ashleigh with the utilization of high-resolution site characterization in South Carolina, with our Q&A section at the end, and then we'll be closing it out there. So with that, I will hand it over to our speakers, starting out with Mr. Sohl. You are first up, so I will make you the presenter right now. And whenever you are ready, you should be good to go.
Hey, many thanks, Drew, and thanks to NUIPIC for their efforts in continuing education for all of us in the industry. And many thanks to all of you for attending today, and hopefully we can generate some good questions from the folks and pass along lessons learned that we've all picked up. Our story at Columbia starts way back in the 80s with the advent of the UST regulations, and we were involved as members in the triage of hundreds of sites in the retail business when the first UST regulations came out. Since then, thousands of stations have changed ownership. The national program was created. Each state developed its approach to resolving the many releases identified in those early investigations. The challenge of unresolved releases, though, continues to today, and we number into the tens of thousands of sites across the United States. As one of the service providers in the industry, we found ourselves going back to the same sites time and time again and wondering, why is that? We've been there before, during, and after remediation, but yet the sites continue to have a life of their own. So that generates a lot of uncertainty and frustration on the part of many folks involved in the industry, from regulators to site owners to the industry professionals, and we end up in a situation where we've got mismanagement, overmanagement, untenable pricing structures, lack of trust, yet we still have contaminated groundwater, and we're spending millions and millions of dollars on this. And we've got millions of dollars of hardware in the ground that seemingly is ineffective. That is the basic definition of unsustainable. It's unsustainable economically, and it's unsustainable environmentally. So if we fast forward a couple of decades, you get to the new understanding in the 2000s of what the academics have learned and what we've all learned about LNAPL and oil in the ground, and the work of the Interstate Technology and Regulatory Council, ITRC. So ITRC embarked on a program of best practices to look at these types of sites. And I sat in, I think, up to about 10 classes learning about the management of LNAPL, which is now most recently outlined in their recent LNAPL 3 online interactive guidance. So even I can pick up some ideas sitting through 10 classes, but it became apparent to me from our experience that the sites were not being addressed in what we call a systematic fashion, incorporating these best practices. So we at Columbia took on the challenge to say, well, how do we develop a systematic program taking advantage of the state-of-the-art tools, high-resolution technologies, real-time analysis tools, and how do we then go in and get a better look at these sites, manage the uncertainty, and zero in on what's causing the problem. And the big aha was we found the reason that the groundwater persistently exceeds site action levels is because there's really a lot of residual LNAPL remaining on the site. And we saw that 100% of the time. And so in the words of ITRC, if you've got a groundwater problem, then you've got a soil problem, and you just haven't found it yet, or all of it. So this afternoon, I'm going to walk through our observations based on a statistically significant universe of about 150 sites across 26 states, provide a couple of simple case examples, and then wrap up with a few recommendations for the industry. So the first big issue is there's almost a myopic focus on the groundwater at these sites and really missing the source of the problem, the actual residual LNAPL. And this is somewhat understandable because the whole program is based on the Clean Water Act, and our metric for achieving success is groundwater. However, groundwater is only an indirect measurement, and it's highly variable over the time and the life of the sites. Gradient flow directions change direction. Monitoring wells are not going to give us all the answers in terms of mass. And it leads to a blinding misdirection of really what the problem is. Petroleum LNAPL, on the other hand, has its own mind. It's going to go where it wants to go. And by definition, it's a non-aqueous substance. And so we're not going to find the LNAPL that's causing the problem in the groundwater. And your groundwater levels are going to change extensively. And so a lot of our monitoring and even some of our remediation systems are installed based on the historical understanding of groundwater, which is highly variable over the life of the sites. So the first real change in direction that we take and recommended was, let's focus on what the residual problem is. Where's the oil, the LNAPL, and what kind of soil is it in, and rather than focusing on the water. But then we learned you really have got to understand multiple pieces of the issue, of the challenge. And you've got to understand the chemistry of what you're talking about, because certain things will see certain chemistry and certain things will not see those things in terms of sensors, detectors, even lab analyses. And so if we're monitoring sites based on the BTEX concentrations of the high risk components, we're missing the majority of the mass that exists on the site that's resulting in the use of the affecting the remedial performance. We also need to understand the soil. We're dealing with fluid dynamics, so we need to understand where is that chemistry and what kind of soil. We need to understand the relationship of the LNAPL to the groundwater. Is it perched? Is it confined, or is it an unconfined scenario? And then we can start looking at, well, what's the relationship between the stable LNAPL and the creation of the dissolve phase that comes off of that. And most recently, in the last few years, have been significant breakthroughs in understanding what's happening in the vapor phase and the actual degradation and dissociation properties that are going on in the sites, oftentimes much more effectively than all the hardware we have in the ground. And then finally, what's the spatial alignment of our remediation systems and our monitoring systems to both the residual problem, the dissolve phase, and the soil structure and the permeable pathways that are down there. So we developed what we consider a systematic approach to take a look at these things. And it starts with leveraging all the information that we've been collected on the sites, which is oftentimes very rich in clues as to what's going on. But then the next big change in direction, as I mentioned earlier, is we go in and focus on where is the residual source material and how do we find that, all of it, and then how do we verify that it's stable, or if it's not stable, what condition it's in. Once we have that mapped out and we understand what soil that it's in, then we can move on to evaluating the groundwater, the impact of the groundwater in dissolve phase plumes. Then we come back and look at, are there potential vapor intrusion issues? And good news is not usually, but can be. And then we look at that spatial orientation issue. And then now, most recently, we're starting to evaluate what is the potential that actually Mother Nature and monitored natural attenuation and the natural source zone depletion and dissociation of that oil is working faster than anything else we can do. Once we have those data sets or those lines of evidence, then we revise the conceptual site model and provide a better roadmap on making the remedial option decisions. So the preliminary findings, and it's a little bit small for y'all to see, but again, out of the 150 sites that are in that universe, we found oftentimes that there was significant gaps in the existing conceptual models. And most of it dealt with, there was a lot of undiscovered, we'll use that term, residual LNAPL out there. And typically, that was because of the jump onto the, we have a release, the groundwater gradient is in direction X, and that's where we focused the industry focused our investigations, was going down gradient from where we perceive the release to be. What we found was often there was more than one release, more than one product, and quite frankly, the LNAP will goes whatever direction it wants to go, regardless of the groundwater, until that LNAP reaches stability. We also generally found most of the residual LNAP was below the current air-water interface. Soil vapor extractions were used heavily in the early days. We're now using multi-phase extractions and air sparging systems, and we're starting to dip into that. But really what we found was typically the iceberg effect. Majority of the mass was below the air-water interface, oftentimes not sampled, not evaluated, and it was permeated into very layered site stratigraphy. So I think we all acknowledge that sites are a lot more heterogeneous than we want to picture in a textbook, but in fact that has a significant impact on the fluid mechanics of what goes on, as well as the retentiveness or how that LNAP was retained in those tighter zones. That leads to issues of preferential pathways of both the LNAP itself until it reaches stability and the dissolve phases. It impacts the effectiveness of any chemical injections. Do they get to those tighter zones, or do they basically go down these higher permeable stringers? It results in redistribution of the LNAP when mechanical vapor extraction, MIMI type events occur, and we're pulling LNAP from elevation A down to elevation B, or across the site, or submerging it. And what we found was, particularly on the old sites, which is mostly what we're dealing with, is that LNAP has degraded and bound itself in and around the soil pores to a stage that it is really not transmissive, not recoverable, and not generally mobile. And so any type of fluid mechanics system that we're trying to use to remove it, or think we're going to pull it past, is really turning out to be ineffective. And then again, I mentioned the misalignment of the monitoring and or recovery well screens. And that could be misalignment in that it's screened too far and it crosses over multiple layers of permeability, to it's screened completely off target, to it's at a lower or deeper depth and it's pulling LNAP down to that screen through the filter packer or a preferential preferential pathway. And then finally, we as an industry have not looked hard enough at the groundwater redox parameters of what's going on. You can map a plume out pretty well using the redox parameters, as well as some of the other things we'll talk about with natural source on depletion. The other thing I'd like to say about the term high resolution site characterization before I go into a case study is it's a lot of times that term is used to describe a particular type of technology, like direct sensing technology, or you hear the UVOST or the LIF or the MIP or something of that nature. But really what HRSC is a methodology. You need scale appropriate information about all those things that we just talked about: the LNAP itself, the soil, the groundwater, the vapors, the constituents, the mass. You need sufficient scale appropriate data in order to be able to make a credible decision about how much mass is left, what kind of constituents are there, what's the degradation preferential that's going on, and what's going to work or not work. So try not to use the term HRSC to think about a particular technology, but think about how do I get the lines of evidence in sufficient detail or sufficient resolution to make the decisions that I need to make. So just a couple of quick examples here. Stevens Fuels' site, really what we found here and what I'm trying to show for you is how thin the layers of the residual NAPL are on the site. We're showing that here in these orange discs, basically. And you can start to see a relationship between the residual LNAPL and what's in a monitoring well. a good thumb rule, again, that ITRC teaches is if you've got a part per million in your monitoring well, then you've got some LNAPL in the vicinity of that well, and you need to find that, or else it's going to continue to be persistent in that well. And your dissolve phase is going to come off of that LNAPL phase. And so, again, if you're mapping only the dissolve phase, you're going to miss the real source of what happens. And so, kind of taking a look at this one in a different view, you can ask yourself, well, if we have a release up at this elevation, do we get LNAPL all the way down here? And we see that we've gone in and installed a bunch of monitoring wells down here in deep, and the actions associated with even installing the wells and or applying vacuum extraction to that will remobilize that LNAPL down preferential pathways if they do exist. That's a simple example, just looking at how distinct the individual layers are. We don't necessarily have a large mass down there in terms of your traditional blob, but it's down there and it's feeding those groundwater elevated concentrations for an extended period of time. This is an example that came to life because we had tank removal and removed a amount of hardware and LNAPL out of the original source area up here in this location. However, well down gradient to the southwest down here, persistent obnoxious fumes were detected, and it passed another piece of property down in this direction. And so the investigation was, well, what's causing that? And that was sealed off, but then where did that come from? And again, if you've got that kind of dissolve phase plume distance, then you've got to go back and find the source area. So we went back and systematically looked at the site and found a considerable amount of mass in a different release area on the particular site. And you can see how that mass on that site, is giving us the readings that we're seeing in the recovery wells and the monitoring wells, but it's also creating or giving rise to this dissolve phase plume that goes down gradient and will be persistent over time. So again, it comes back to this mass is well below the air-water interface. It's below this tighter zone shown here in the darker, and it's yet undiscovered, but the clues are there that type of material is there. And so that's what we're looking for in this systematic approach. This site has about a 15-year history and several $1 million of investigation and remediation accomplished, yet had persistent groundwater down gradient. This is the tank pit area back from when the tank was originally removed. And you can see left in the ground is tens of thousands of milligrams of TPH that, in the walls and the floor of that tank enclosure. And you say, well, is that enough to cause the problem that we're seeing? Well, we then went in and again systematically looked at a plot adjacent to the area. This is the original tank pit area. And then we looked at the adjacent area that was accessible with fluorescence tools. And we found, again, a considerable amount of mass in that. And then that passed on. Again, we see the groundwater plume delineating or being created off of that and going down gradient. So despite literally years and millions of dollars, we still have this groundwater plume. But then the question is that an issue? And so we took it to the next step and looked at, well, what is the degradation rate of this mass back here in this particular area? What is the transmission rate or mass transfer rate in this groundwater axis going down this direction? And do we have a sufficient monitoring well network to basically say we're protecting down gradient receptors? And so you can use a series of data, again, using your groundwater redox parameters. In this case, we did redox parameters. We looked at VOC concentrations. We actually measured source zone depletion rates in a couple of different methodologies, and pretty well established. Yes, we've got clean water coming into the plume area, it passes through and gets degraded, and then it comes out the other side and starts recovering. And we've got a sufficient monitoring well network to protect the down gradient receptors. And so a decision could be made, well, we don't really need to do anything else, but we're going to change the metrics by which we're monitoring this particular site. I'll come back to the three-dimensional picture of that, assuming we have time later. But so once we looked at all these different sites, we said, so why are we in this situation, and what recommendations would we have to the states when we were asked to look at this for the states? And oftentimes we found in many of the states, there's not a mechanism to identify stalled or failed remediation projects, and there's not a mechanism to go in and reevaluate that conceptual site model, because the cost structures or the reimbursement structures are all based on, sort of the original site characterization game plan and then the remedial activities. So our recommendation to the Office of Underground Storage Tanks and to the states was, think about how you can triage the sites that are performing or not performing and come up with a mechanism to evaluate them, set performance metrics that target the performance of that remediation system, and then think about how to do these high resolution sort of diagnostic evaluations of these sites in order to gather what's causing it to hang up and or not performed. So that's really what those 3 points talk to. Our recommendations is, and then again, this was to the Office of Underground Storage Tanks, is encourage really looking at failed install remediation sites. The data basically says if we're not recovering fluids, the oils have degraded to such a point that fluid recovery is really not going to work, and alternative approaches need to be evaluated. There's a lot of guidance within HRSC. There's a lot of guidance from API and other folks that talk about that. And so the basic structure of LNAPL 3 is a good management tool for sites, and then set the lines of evidence that go around that. If you're considering any sort of what I would call expensive remedial activities that are going to involve significant changes to the groundwater levels, involve injection of chemicals, trying to put in extensive mechanical systems down there, then you really do need to get HRSC done early, identify where the residual LNAPLs are, identify its ability to be removed, what kind of soil is it in, what's its concentrations, and think about it from that perspective before you write the check to go start doing a whole bunch of other things that are likely not to be effective. The fourth bullet here is one that is often ignored and sometimes prohibited by the cost structures and or the regulations at many state levels, is in order to understand that LNAPL, you've got to understand what it is, what its mass is, what's constituents that make it up or made up in the LNAPL, and understand how it's going to degrade or how it has been degrading. And so in order to do that, you've got to go in and do what I call saturated soil sampling in a systematic fashion below that air-water interface, and then measure the total hydrocarbon mass, as well as a couple other parameters in those protocols in order to get to the right answer. Otherwise, you're only guessing what that TPH or total mass is. And so again, incorporate TPH analysis back into our analysis and into our investigations. And then I'm just really want to emphasize the concept of natural source zone depletion. The body of knowledge is growing on that rapidly. The amount of data that's being collected is telling us a lot more. But if you think about how old the oil is and how ineffective the fluid recovery systems are, you can also think about it from a business perspective. What are we going to do post-COVID, tight budgets, future clean energy? The money available to keep putting hardware in the ground and having to do the O&M on that is not really sustainable. And so we really need to get a better handle on, can we use natural processes and set metrics on removal of mass by whatever system we use, either natural or mechanical, to really take a look at the effect of reducing that LNAPL in its impact to the groundwater. So I believe I'm going to stop there and see if there are any quick questions, Nick.
Great, yeah, thank you so much for presenting on that. We do have a few questions. Quick reminder to our audience, please use this time to input any questions that you may have for John in the question box. But the first question that we do have is someone asking where the 150 sites are.
Again, they were across about 26 states in the United States. That's within that inventory.
Okay, great. Next, we have a question. John, can HRSC measure CO2 and methane during the investigation to estimate national source zone depletion?
Again, we think it's a critical part of the HRSC protocol. So the answer is yes. And it would be important to do that once you've found the LNAPL, all of the LNAPL, because your natural source on depletion is going to occur above your LNAPL bodies within those permeable, vertical permeable pathways. So once you map the LNAPL, then consider your PVI, consider your dissolve phase, but then consider your natural source on depletion measurements above the LNAPL body.
Great. And another question, please discuss the reason for TPH sampling.
So TPH really, a lot of people, there's a lot of different definitions of total hydrocarbons, but the real key is what is the total hydrocarbon mass that any remedial activity is attempting to correct, because it's not just correcting the BTEX and or naphthalene components, it's using the oxygen exchange, electron exchange to change with all of the total hydrocarbons that are down there. So without understanding the total mass, it's very difficult to address what the stoichiometrics are really of reducing that mass by whatever methodology you're using. And so, and a lot of the research that's been done about the potential mobility and or recoverability of the oil or the transmissivity of the oil are based on total hydrocarbon mass, not just a couple of constituents within that mass. So if you want to use any sort of screening or performance metric, you really have to understand what's the total mass and what are the constituents in that today and at different stages in the degradation life cycle.
Great. And quick reminder to our audience to please address all questions to a speaker. So it looks like this might be the last question that we get to. What kind of data is optimal for measuring source zone depletion and can make inferences about natural attenuation by doing this?
Well, I would refer you to the API guidelines and I believe in ASTM guidelines on natural source zone depletion. And again, that is evolving in real time now. And so there's a number of different methodologies to use that. One is to measure the CO2 gradients. So if you've got oxygen infiltration, you've got the creation of CO2 and methane NVOCs coming off of the LNAPL body, you can measure those gradients over the LNAPL body at multiple depths and do both, one, prove the fact that depletion is occurring or not occurring, and two, you can measure the gradients and then come up with a quantitative measurement. There are a number of methodologies for measuring CO2 flux, and that's the flux that's being generated by the LNAPL degradation compared to natural CO2 flux that's occurring. And so there's a couple methodologies within those guidelines. And there's new work looking at measuring temperature gradients of the degradation. So you could theoretically instrument your LNAPL body and monitor the change in temperature trends as degradation occurs over the life cycle of the plume. And so again, that's a very evolving area, rich for new information and new data, but there are a few proven methods at this point in time. And there is, in fact, LNAPL degradation models. Again, when you go into modeling, you've got to make a lot of assumptions. And so my personal preference is on empirical data, but There again, there's somebody wants to send me an email, I can point you to 2 or 3 guidance documents that have got that stuff on a global scale. So the Australians have got a nice package, Europeans, as well as some of the stuff from the US.
Great. Thank you again, John. I really do appreciate that. With that, we will hold all these questions for the end. Definitely seen a lot of great ones, and I will take the steps to transfer control over to Dorothy. So please bear with us as we get this organized. All right, so Dorothy should be able to take control whenever you're ready.
Well, greetings from the Malaier dining room table in Montgomery, Alabama. I hope y'all are all well out there across the country. I appreciate the opportunity to share with you a strategy that we're using in our UST Corrective Action Program to provide for more effective and efficient cleanups. I'm Dorothy Malaier, and I currently serve as one of the section supervisors in the UST Corrective Action Program in the Alabama Department of Environmental Management. Since the first site assessment arrived in our offices in the late 1980s, if you remember those days, the procedures to obtain subsurface data at release sites has evolved with time. While the primary focus remains on measuring for concentrations of petroleum constituents in the soil and groundwater, the available tools and procedures to better understand the migration potential and extent of the contamination have definitely evolved. It's always been about data. How much data do you need? What data do you need? What data really makes the difference in decision making? The use of high-resolution site characterization investigations at Alabama sites continues the quest for data. We utilize the characterization process at different stages in the assessment and remediation process. Today, I will share with you some of our sites and the strategies we are applying in response to the data obtained from the high-resolution investigations. As with most states, one size does not fit all, and one methodology does not fit all. Alabama is blessed with a variety of geologic settings. Each setting has challenges of its own in regards to the fate and migration of contaminants. The southern part of our state lies within the Gulf coastal plain, where we have underlying sediments of sand, silts, and clays, often discontinuous. UST releases located within the Piedmont area are often challenging. The migration of contaminants within the metamorphics often are unpredictable. The valley and ridge is underlain by sandstone, chert, shale, limestone. Contaminant investigations in bedrock are difficult, and the remediation is even more difficult. The highland rim of North Alabama is underlain primarily by limestone, and the weathered zones above the bedrock can be layered and have multiple preferred pathways of migration. So due to this variety of geologic settings, there's no one way to assess the sites, but the more data that you can obtain on a detailed level, the better. And this is where high-resolution site characterization comes into play. Since records were first kept, Alabama has recorded over 12,000 releases from UST systems. About 5,200 of these required additional assessment and remediation and received a UST release incident number. A tremendous amount of progress has been made in performing cleanup at the sites utilizing a risk-based corrective action approach. Our approach was modeled after the ASTM Rebecca protocol and is still in use today. Our workload today is illustrated on this pie chart. Of the over 5,200 UST release incidents, we've been able to issue letters of no further action to over 4,300. But the remaining incidents are either in an inactive status where we have no viable responsible party, in investigation, in monitoring, or they have an approved corrective action plan. Of the 913 open release incidents, 510 have approved corrective action plans. Some caps were approved within the last year, but others were approved many, many years ago. So our challenge today ultimately includes addressing a significant population of inactive release incidents. The other emphasis is on completing cleanup on the 510 incidents in a cost-effective manner and efficient manner. Improving the remediation efficiency and cost effectiveness is vital for these 510 releases with approved corrective action plans. For those sites in monitoring and investigations, there's great need to have adequate data for decision making to determine the risk of the site and to serve as the blueprint for developing a corrective action plan that uses appropriate remediation strategies. So the use of high resolution site characterization can be applied at any site within any of these various site status categories. Well, why do we continue to have so many sites of such an advanced stage? Some of these are in RNA monitoring, because that's a very cost-effective way to do remediation. So the time to meet site-specific target levels can take a long time. Others have engineered cleanups that are just maybe not that effective. Well, why are they not effective? Well, maybe it's just poor operation of the system. Maybe the sites are just kind of on an autopilot operational status. But is there more contaminant mass present in a different area or zone than was originally identified? Probably so. So the scene is set. You've got a glimpse at our UST cleanup challenges, but we still have work to do to complete more cleanups. And so there are 3 pending questions with us. How do we increase the number of cleanups and have more NFAs issued? And how do we decrease this cleanup time? Some of our sites take a long time to get to cleanup closure status. Are we using our time and resources on cleanup strategies where we really don't understand the subsurface conditions? What could we do? What could we know that we don't know right now? What could we do that we're not doing? And do we need more data in order to answer these questions? So I have 5 sites that I want to talk to you about today. And a very promising, and so far, I think, effective technique that we've been using is the use of high resolution site characterization to enhance our knowledge base. And we've been authorizing these specialized investigations for about 6 years or so. And today I'll share with you why and how we utilize high resolution site characterization at 5 of our sites, all in different parts of the state. And for each one of those, we were trying to seek new data to try and answer somewhat different questions. And I'll share with you things that we learned along the way as we've been utilizing this process. My presentation is not about how the technology works, but when we perform the investigations, how we use the new data and observations collected from a program manager's point of view. In January of this year, just a few months ago, a complaint of petroleum vapors in a nearby church and hotel was reported. A report of vapors in a church, school, or any building is certainly a call to action. The investigation into the source of the vapors is often complex. In this site that I'll talk to you right now, it had at least 4 gas stations historically located in the area we thought was the source of the vapors. But, to start with, was this actually a UST release into the sewer? Was it a car accident that released petroleum? Did somebody dispose of petroleum products into the sewer? We needed to find out these answers to these questions. So as the emergency response began, it was determined that a gas station had been the source of a previous release incident, and it was remediated and closed out. Very close by, there were 2 closed out UST release incidents across the street that were closed out about 5 years ago. And then another active gas station across the side street. An initial response was performed, and it was determined that a release had occurred from the dispensers at an operating gas station about 2 blocks away from the church that reported the vapors. Local authorities reported that visible free product was observed in the sanitary sewer. Those lines were flushed by the fire department. Required system testing revealed that there was a slow leak from a flex connector under one of the dispensers. Exhaust fans were placed on manholes, and a drilling program was started immediately. Monitoring wells were drilled, and a MIMI event, which is a mobile enhanced multi-phase extraction event, was performed for a 96-hour stint and a 24-hour stint. The consultant recommended that a high-resolution site characterization be used to better define the contaminant mass. So this was one of our first high-resolution site characterizations performed at the early stage in an investigative process, and it became part of the initial site response. So the high-resolution site characterization was designed to be a part of the emergency response in January 2020. We actually had the investigation performed in early February, just a few weeks after the release was reported to start with. So the purpose of the study was to accurately delineate both vertically and laterally any residual light non-aqueous phase liquid at the site, to identify the soil structure in which any LNAPL might reside, look at the permeability and potential for recovery, and to identify potential pathways from the source area to the sanitary sewer. And all this was happening very dynamically, with the release being reported early January, wells put in early January. An actual remediation system was installed by the end of January. And we did the high resolution study at the beginning of February. So very dynamic and a very quick response. So a high resolution investigation provides for real-time data collection of various parameters and can be presented in a visual manner that contributes tremendously to the site conceptual model. As you know, interpretations of data by individuals can vary significantly. The amount of data collected and the level of data level of detail of the person collecting the data can vary from technique to technique and from person to person. And in old geology terms, are you a lumper or are you a splitter? Do you observe and document things in a more macro way, or are you more in a micro way, more of a splitter? So a simplified cross section with only a few points using site observations by field personnel are a traditional part of the typical site investigation, and will still always be a part of the multi-pronged data collection process. But you have to admit the data set is limited when compared to the data set of a high resolution study, where thousands of data points are collected. So this is the same site. So this slide shows a much more detailed presentation of data collected from the site. You can even see the location of the sewer line that was projected onto the site diagram to further enhance the site conceptual model. You can see the varied soil types, layers that are expressed compared to the previous cross-section we had. Again, it is all about additional data collection. The high-resolution investigation data presentation and measurements may be more consistent than human observations and could add greatly to the site conceptual model. Multiple technologies were actually applied at this site using an optical imaging profile or hydraulic profiling tool. Those were used to isolate and characterize the primary source areas from potential source areas of migration in each direction. The tools were used to evaluate the subsurface hydrostratigraphy in the area of the release, identify higher permeability layers or heterogeneities that often constitute preferential pathways for the movement of LNAPL or dissolved phase contaminants. We performed about 20 borings at this site. The borings advanced to the site show predominantly lower permeability soils consisted with the interbedded clay and silt, with traces of sand reported in borings drilled from monitoring well installation at the site. Electrical conductivity measurements were also indicative, predominantly low permeability soils. The high-resolution study indicated that LNAPL is present in multiple locations from approximately 15 to 22 feet below land surface, with the most occurrence of LNAPL, obviously, in the vicinity of the dispenser islands, extending east toward the sanitary sewer line along 6th Avenue. There was no indication of LNAPL found above the sewer line at the site, and in general, the observed LNAPL was about 5 feet below the sewer line, which was interesting. But as you know, sewer lines and the backfill around those sewer lines often are the transport mechanism for vapors. Based on the results of the high-resolution study, the consultant recommended that the newly installed recovery well MW10 be over-drilled. It wasn't deep enough, based on this data that we collected. And they're going to reinstall it, make it a little bit larger diameter well. And it's all based on this particular study. So the use of the high resolution was one of several responses to the site as a multi-pronged approach. By using the high resolution investigation very early in the remedial design and emergency response, we're hopeful, hopeful that the ongoing remediation will be more effective and efficient. Another example is how we use high resolution studies to see if there are multiple sources in an area. At a site in Theodore, Alabama, which is down in Mobile County along the Gulf, we have the scenario of having a gas station on just about every corner. In fact, within the immediate area of this release, there were or are over 7 gas station locations. Determining the likely source of the contaminants, either on-site or off-site, was the focus of the high-resolution study. Was there migration from other sites onto this gas station, or was there a release that migrated from this gas station onto other properties? So the results of the high-resolution study, combined with traditional soil and groundwater investigation data, revealed that a relatively new release was discovered right around the dispenser island. There was a new release observed. That release received its own incident, and free product was removed. The data also indicates that the higher groundwater concentrations are actually present in the red areas identified here on the far east end of the property, and then on a parcel to the west. The high-res study reveals specific zones that could be targeted with a MEME event to remove that free product that was observed in the well near the dispenser. And again, you can see the enhanced depiction of the subsurface using the high-res data. Some of the high-resolution studies include the drilling of additional borings and soil samples collected to compare to the data collected during the high-res data collection. The combination of traditional data collection with the more advanced techniques provides for a very comprehensive data set and can serve to confirm the data collected from the downhole tools. By combining soil contaminant concentration data with the results of the hydraulic profiling tools, it is not uncommon to have low permeability zones identified, which may be serving as an area of low transmissivity, leading to an interpretation that while contamination may be present, it may not have a likelihood for significant further migration. So the result of the investigation supports the conceptual model that the higher concentrations to the southwest and northeast may have been sourced by different sources. All data was utilized for interpretation and to update the site conceptual model. From the original soil data collected, groundwater data was evaluated over time. We observed free product, subsequent removal of that free product, and the data that we collected from off-site properties is led to the conclusion that there may be off-site sources for the contamination in those wells that currently have the highest dissolved contaminant levels. So going forward at this site, it does appear that there are some other sources, perhaps off-site, for these higher concentrations that are seen today. We are continuing with the monitoring program to develop an even larger data set, and we're looking into some deed documents to determine if some adjacent properties may have been used for fuel storage in the past. So the next example is an example of an old incident and what you might expect at a typical site high-resolution study. This one is located in Tuscaloosa. This particular site enlightened me as it was the first project that I was able to be present on site and to utilize a computer-based data sharing program that allows various parties who aren't on site to collaborate on the project. Many of our older sites, excuse me, are being investigated to determine if we have missed contaminant mass. Kind of like what John was saying, we have a lot of old incidents, a lot of hardware in the ground. Why aren't they getting cleaned up? So this particular site dates back to the early 90s and has used several remediation technologies for cleanup. It was obvious by the consistent data that was being collected at the site that we may not have the best understanding of the location of the remaining mass. We wanted to know more about the potential location of mass at the site that seemed to be continuing to contribute to the elevated groundwater concentrations and preventing closure of the incident. The original site conceptual model was based on a series of borings and the interpretation of that data in singular boring logs and also in a rather nice fence diagram that was produced in the early 90s. But the level of detail in these presentations is limited. With the age of the release and the fact that a USC system has been on site since at least 1967, there could have been more recent small releases over time that have prevented the concentrations to degrade or reduce as expected. So could we use the high resolution data to shed a little light on this thought? The cost to perform various activities is often influenced by the risks posed to the site and the prep work needed before you even begin collecting the data that you're seeking. This site is an active gas station and a very busy one. Dodging cars, filling up the pumps was a challenge due to active piping and tanks at the site, and the way the site was located on somewhat of a point, the need to clear each borehole by hand was a necessity, and that's represented by the picture in the upper left. As I recall, the crew was encountering gravel in the borehole at shallow intervals, and this really slowed down the borehole drilling. To top it off, there was construction next door, and it was in the middle of August, very hot, humid month to be doing work. So sometimes the projects can take a little bit longer than anticipated for various reasons. But a lesson noted that, you can perform these types of investigations on abandoned sites as well as active gas stations. But you have to be prepared to address the safety and congestion presented to the site, and it may take you a little bit longer to do the investigation. The slide also represents the need to plan early to decide on the type of data that you want to collect at the site. Most of the high-resolution vendors offer various tools that can be utilized in data collection. It's critical to discuss during the planning stage with the regulator, contractor, and vendor to know what your data objectives are, limitations that may exist, and the level of data presentation that you want in the final reports. The presentation of the data can be an added expense to the project, and you need to determine early what data presentation is necessary for the site in question. What do you want as the final product? The figure to the bottom left is kind of like the Wizard of Oz, pulling back the curtain. How do they do this? So basically, you have an operator in a van full of equipment, computers, data screens, and the visual display of the data collected at the site is an integral part of the investigation. The vendor at this location in his van has all the tools and computers located inside. And the operator is monitoring the data continuously, and it can be viewed on site by other site representatives. This is truly real-time data. The ability to view a zone at a precise depth that indicates the likely presence of LNAPL is information, and it's very exciting if you're there. You can finally see what you have not been able to see to help clean up the site using the limited data that you've had. Even though you may have had 30 years worth of data, I think we got as much data in this week-long investigation as we may have had over the last 30 years. The fluorescence of LNAPL is clearly seen on the computer screen at a depth of about 17 feet and indicates an area of residual LNAPL that's still there after 30 years. This visual representation of the data enhances the knowledge of the site and can allow for a more focused approach going forward. And data presentation is key. One benefit of the high resolution site investigations is the addition of a tremendous number of new data points and metrics. For example, at the site, we're able to perform an additional 26 borings that provided additional data with the hope of enhancing the remediation and decision making at the site. Cross sections are readily prepared that can provide an enhanced view of the subsurface. We can finally see what's underneath the ground. Zones of interest can be easily identified at the site. And now the site conceptual model is more easily updated for future decision making. So after spending a day at the site in late August where it was extremely hot, I went back to the office, and being in the office was a treat. Remote viewing of the site work is one of the most helpful aspects of the high resolution site characterization. I was able to be at the site to observe some of the field work being done, but when I returned to the office, I was also able to continue to be a part of the site investigation by connecting through a portal and seeing real-time data collection. This is my desk. I haven't seen it in a while, but it's still there. And it has a display on the monitors. While waiting on new data, I was able to do some other things, take some phone calls. But I could see the progress of the site and continue to provide input. So this process allows for continued collaboration between the high-resolution vendor, the on-site consultant, the tank owner, and the state regulator. Very dynamic. So where are we after this investigation? So we're going to keep the DPVE system off that was on there originally. We're doing some periodic MIMI events in the vicinity of the well with the highest groundwater contamination. The site is much better delineated now, and there's an evaluation being performed for a future remedial method, maybe injection. Because of the amount of data that was collected, doing some type of injection remedial action, I think you're going to have a more successful outcome. The next site provides insight into how the high-resolution study can provide focused data on a very old release incident that after 27 years still has benzene levels as much as 24 milligrams per liter benzene last year. It's pretty high after over 20 years. So we knew there had to be L-NAPL present, but we didn't know really where it was. So historic data indicated that while the plume was contained laterally, the continued high levels of contamination indicated that residual free product was likely present. And we had kind of a classic bullseye plume on the site. The investigation revealed that the soil was heterogeneous, but that's not uncommon in Alabama. There was also evidence of pinnacled limestone. Site wells were screened at different intervals, and both shallow and deep wells contained significant contamination. So the examples I'm discussing today are from various locations within the state. Some are easier to drill than others. At this site, you can see the bent rods. Well, there were multiple refusals, and bent drill rods and subassemblies were encountered while using direct push technology, confirming the uneven nature of the subsurface. It was difficult drilling. Pinnacled limestone was encountered at the location and made drilling very difficult. But that's probably one of the reasons why this site is over 20 years old. But despite the difficulties, important data was collected. The high-resolution study was able to delineate areas of L-NAPL at depths of 32 to 45 feet deep. Benzene concentrations in a monitoring well in that area recently were measured as high as 14 milligrams per liter, still very high. And even the latest sampling event, free product, was finally observed. The study confirmed that various intervals have significant contamination, some present in low permeability zones that are likely storage areas. However, higher permeability zones were identified that may be the preferred migration zones. Using the optical imaging profile and hydraulic profiling tools, the investigation was able to delineate the L-NAPL at depths as shallow as 4 feet and its deep as around 30 to 45. The OIP tool was able to show where the free product was stored. The blue image here shows visual observation of the L-NAPL. It was actually a video taken of these measures, and it was quite impressive with the way that the tools are able to identify the L-NAPL and how it's displayed. So going forward for this site, we're able to install new recovery wells, though it was difficult because of that pinnacle limestone still there. And recently, almost a foot of free product was observed in the site well, one of those that had the really high benzene levels. And MIMI events are going to be performed to remove that free product and see if that won't help reduce the dissolved concentrations in a much more focused manner than we were doing previously. So we have a better understanding of the site and have indeed confirmed that L-NAPL is present and is why we still have high dissolved. The next site is a very large release site down in Spanish Fort, Alabama, in Baldwin County. It's located near Mobile Bay. The bay is a sensitive receptor, and cleaning up this plume is a priority. There was a need for additional information to gather data in support of a modified approach to the cleanup. Multiple releases were identified at the gas station, which now no longer has operating USTs. But this investigation provided new insight into the subsurface and provided for a better focused remedial approach to be applied at the site. The focus of the high-resolution study was to better understand the various sources at the gas station that may have contributed to the contaminant mass. The plume shown on this slide has been as long as about 700 feet. Difficulties addressing the contamination include the use of the neighboring properties as a daycare center, some residences. There were multiple releases. The depth to the groundwater is about 42 feet. There's a very busy 4-lane Highway 98 in front of the station, and there were impacts to multiple properties. Very permeable sediments, very transmissive. The cleanup of the site has always been a multi-remedy approach, and while significant cleanup had occurred, it was clear that more data was needed to be collected to better understand the subsurface and flow pathways. As you can see from this cross-sectional view, the high-resolution study was able to identify mass at varying levels, which had not been fully understood before. This was a game changer. Residual LNAPL was detected in just about all of the probe holes on site and on the property west of the gas station. Fortunately, the bore holes across the street really didn't show much residual LNAPL. The presentation of the data collected through the high-resolution study more clearly shows areas of the site that need further remediation. In this slide, you can see clearly several layers of contamination that require further remediation. So the various high-resolution vendors can customize what data presentation you'd like to have for the site. While there's a cost for more detailed interpretive data, it may pay off in the long run if the location of the contaminant zone is more clearly depicted and a new remedial approach can address the various areas. So the data collected during the high-resolution study provided new information that resulted in a modification of the existing CAP at this site. The data collected can be presented in a fashion that allows for a better understanding of the subsurface. Identifying zones of higher permeability and often higher contamination may identify the areas for screened intervals of recovery wells to be installed, or perhaps the preferred intervals for an injection of air, ozone, or some other product. So going forward after the high-resolution study here, there was a modified corrective action plan developed. It actually includes the installation of some horizontal wells to focus on zones under the highway. New recovery wells are being installed on site, and a new DPVE system will be installed. SVE wells are going to be installed to address the more shallow intervals identified during this study. So all in all, some observations from high-resolution studies that have been performed in Alabama is that, you can run into property owners that might be concerned about all the numerous probe holes. You're getting a lot of data. You're using the geoprobe and probing quite a bit, but usually that can be addressed reasonably with the property owner. And you do need to select the tool suite that will provide the data you want. Do you want all the data you can get, or do you just need certain types of data? The right-of-way along the highways continue to reduce the ability to honestly define the plume sometimes, so you're still limited on some of the projects. And active stations are sometimes difficult to drill because of all the existing substructure there. Utility corridors can often be a barrier, as they are with a lot of different tools that you use out there. And of course, direct push rigs have some limitations. And some of those limitations might be running into pinnacles and bedrock, which can reduce the effectiveness of site investigation. But important thing is that this is all about collaboration between all the parties. Having all the parties being well educated on just what this type of investigation can provide is key. You also want to be sure that consultants are able to use the data for them to make different decisions. And it's a very dynamic process. You need to be flexible and realize that it's a real-time data collection with real-time decision making. So in Alabama, over 88 high-resolution studies have been approved or performed, and we've spent probably over $3.5 million on this technique. The average cost is about $42,000, and that includes having the investigation done, having a consultant out there, sampling data, and so forth. But all in all, the information that we are able to collect from this type of technology and technique is very, very valuable into our site decision making. Thank you.
Great. Thank you so much, Dorothy. I really do appreciate the presentation. Again, we are going to have a few minutes for Q&A, and we can go ahead and start with this one. Do you agree that all USC release sites without thermal treatment or excavation, some residual mass will remain? So will the state's position. So will the state's position on condition for NFA decisions?
Well, it's very likely that you're leaving some residual LNAPL or residual contamination at almost all the sites. We are a risk-based program in Alabama, So just by having that as our guiding structure, we are leaving certain concentrations of contaminants in soil and groundwater, but the key is making sure that those concentrations are acceptable and will not have an unacceptable risk to the environment or human health. So I guess the answer to that is yes, there may be residual L-NAPA left, dissolved concentrations left, but it's all about getting data, making the right decisions, checking your receptors, and being sure that you're cleaning up the site to the appropriate level.
Great. I think this might be a follow-up question. What is Alabama's requirements regarding the amount of residual mass allowed to achieve site closure?
Well, again, we primarily use the Rebecca approach. We have our own Alabama Rebecca, and we have values calculated that show whether in groundwater or in soil, what are the acceptable levels to remain. Now, sometimes it's very difficult to even achieve those risk-based levels. So we are using other tools like the high-resolution studies where some additional information is being provided that may show with the type of data we're collecting that even though we have concentrations above a site-specific target level that was calculated, it may show that we can leave contamination levels that are higher than those in place, and they'll still be protected.
Great. Maybe one or two more. What are the what percent of your active releases are 20 plus years old?
Oh, I'm not sure if I have that figure off the top of my head. Let's just say we have more than we would like, and it is a significant number. But I don't have that figure off the top of my head. I'm sorry about that.
Okay. And last one, can you share cost details from the gas station HRSC investigation?
Which one? I'm not sure which.
Oh, okay, yeah, and you had a few, so.
Yeah. Okay.
So
well,
yeah,
I mean,
maybe we'll, sorry, go for it.
Well, I can say that on average, I did a calculation, and doing one of these typical investigations, it costs around $42,000, and that's the vendor himself, the GeoPro, the consultant being out there almost the whole time, any analytical data that we need from additional soil borings collected or groundwater sampling that we may do. So that whole package on average is about $42,000. And one way I looked at this when we decided, that's a lot of money. That's actually a lot of money. But when we have remediation systems that have been running for a long time and we're not making the progress that we need, I kind of looked at this as, well, that's the equivalent cost of maybe 1.5 quarters of O&M or maybe 2 quarters of O&M. And if I can use that money to get better data now, maybe we can eliminate some of those O&M costs on the tail end. And that's kind of how we decided to go forth, because we realized if we have better data, can make better decisions, make modifications, we might come out better in the long run with this additional data.
Great. Thanks again, Dorothy, for the presentation and answering those questions. Now we have Ashleigh Thrash on the agenda. So I will go ahead and make Ashleigh the presenter. And Ashleigh, whenever you're ready, you can take it away.
Okay, thanks. And thanks to NUIPIC and Nick and Drew for organizing this and asking me to participate. It's a great opportunity. So my name is Ashleigh Thrash, and as Nick mentioned before, I manage the assessment and non-permitted petroleum section of the UST Management Division here at South Carolina DHEC. And what I'll be talking about today is kind of more of a, 30,000 foot view of how we implemented HRSC and our program, and just the process of kind of how we got our project started in our state. And then I'll go through one brief case study, and then I'll talk about what we thought, the results and the benefits were for us, and then some of the lessons that we learned going through this project. Let's see. So I guess why did we decide to implement this? So one of the goals that we always strive for in our division is continuous improvement, and we felt like this is just one of those things that, utilizing modern technology will improve our assessments and our cleanups. And one thing that kind of spurred that on was the contracting community, started the conversation. Really, several contractors, were asking us about using this technology, and we had very little experience with it in our program. It had been done at several sites, maybe on the non-permitted side of things, and as well as maybe sites where they were being funded by insurance and that type of stuff, but very limited amount of sites. And we just wanted to gain more experience and, make sure to apply it appropriately and just gather enough information to be able to see how it could fit in our existing, rate structure. And, as John talked about, that's a challenge for a lot of states, and, it's no different here. So, a lot of our sites have data gaps and incomplete assessments, and they end up moving back into assessment after they've moved to corrective action, and after having undergone some type of corrective action, whether that be active remediation or more passive types of remediation, or periods of monitoring, verification for monitoring natural attenuation, and finding out that maybe the plume isn't necessarily stable. And when a site does need corrective action, often we find that there are maybe low amounts of bidders, or that contractors give us feedback that there are data gaps, or that they feel like there's a lack of understanding of the LNAPL, residual LNAPL, or dissolved distribution. And I did pull some numbers on our corrective actions and those that actually achieve the remediation goals in the proposed timeframe. And only about 14% of those have achieved their remediation goals in the original proposed timeframes. And as John and Dorothy had mentioned, there is a lot of sites that stick around for a while due to some of these challenges. In our program, there is approximately 52% of our open releases that are 25 plus years old. So, some of our goals were to improve our site conceptual models, and pick the appropriate cleanup strategies, and have more targeted, optimized approaches, and try to get some of these sites closed. So when we decided to do this, we wanted to do it right, and we wanted to make sure to do the appropriate amount of research. And we just wanted to see what was available out there. So prior to this, already, all of our new employees already participate in the HRSC 3-part LNAPL course as part of their onboarding. So that was already going on prior to this. And we were sending new staff as it became available to EPA's 2-day course on HRSC in person if we could, if it was feasible, if it was offered regionally. And if not, if there was an online course offering, we would send them to that. But then recently, last September, we were able to organize a larger class and actually here in Columbia for 14 of our staff to attend, as well as we collaborated with another division here at DHEC. And so we were able to send quite a few folks to that training in collaboration with EPA. So that was a pretty good success. And here's a picture of that training. Obviously, this is before our new normal with social distancing and whatnot. But and then also what we did was we reached out to contractors in the region who implement this technology, regionally, and we met with them and discussed some general pricing for the technology. Just some questions that allowed us to contemplate maybe how this might fit into our existing rate structure, if it even would, or how we could maybe implement this, like what daily rates were, how much footage can be completed in a day, et cetera. And then just learning, generally about the tools and how they work, and what type of sites typically that they do work on. So our goals, when we set out to, complete HRSC at USC sites in South Carolina, we wanted to learn about the technology in general and the application at USC sites in South Carolina, train and empower our staff to use these tools, explore the cost versus the benefit of the tools, because they do, they are expensive, more expensive than traditional assessment tools. Fill in data gaps at sites with incomplete assessments and sites that, were hanging around for quite a while with persistent residual LNAPL or dissolved plume, and gather information to optimize cleanup strategies, determine the limitations of the technology, determine the best use of the technology, and where we could apply it appropriately at our sites. And then one of the major things that we potentially are exploring is gathering information for potential rate development or rate structure for more widespread use at our sites here in South Carolina. So how we went about this is we conducted what we call a pilot study, and we basically wanted to gather enough information to achieve all of our goals. And so our statute and our regulations require us to develop rates for routinely used site rehabilitation technologies or activities. And typically the way that we choose to do this is in accordance with competitive bidding state procurement regulations. So we put 2 contracts together for solicitation, and we did that so that we could maybe get some variability and maybe some different contractors. And so we had 13 sites on each contract, so 26 sites total, and those contracts were put out for solicitation for 30 days and awarded to the lowest responsive and responsible bidders. And we also, in those contracts, it was important that we put in there that we wanted to follow up with traditional methods to confirm the results of the HRSC and supplement the data that was collected. So going on, talking about the site selection. So how did we select our sites? So some senior staff members here in our program went through a pretty rigorous process of selecting sites. We did have to select state lead sites, so just orphan sites or sites where owner operators had selected for us to oversee site rehabilitation. Reason being is that we had to utilize a state lead contract for this in order to gather the information for rate development. And so our strategy for selecting the sites was we wanted to select sites where direct push technologies had performed well, and we hadn't previously had refusal issues because of shallow bedrock or heavily compacted or consolidated materials. But we did want sites that had varying geology as well. So we just choose sites all over the state. And then we wanted sites that had been around a long time and, like I said before, had lingering residual product or dissolved plume, despite corrective action being completed or continued monitoring. And we also wanted to have sites that were in different stages. So maybe they were new sites or no assessment had been completed, or there was some assessment but still some unanswered questions, or we needed maybe just some additional source area characterization, or they had been in corrective action previously but it had not succeeded. So we just wanted sites in every stage to try to get a good sampling and some information. So we were able, since we had 2 different contractors, we were able to see kind of a contrast of the different tools. So we were able to see like the UVOS versus the OI PHPT, and then follow that up with some of the traditional field screening. And then we got to see the Smart Data Solutions, which was the portal that Dorothy was showing earlier. And then we got to see that versus like Rockworks and 4DIM the modeling. So we got to see a good sampling of the different technologies. So that was good. So case study I'm going to talk about is Larry's Body Shop. So this is in Lawrence County in South Carolina. This is kind of in the Piedmont region. So igneous and metamorphic rocks and boring logs indicated a range of saprolitic sandy silt and sandy clay. This is a fairly old release. It was reported in 1991 at a tank closure. There was 3 USTs abandoned by removal. And previously there was an excavation that had occurred. And the details of the excavation are pretty spotty. Some of these old files, you know, it's kind of hard to find specific details of some of this stuff, but it basically mentioned referencing excavating at the tank basin. So I'll show a figure here in a moment. But it did go down to at least 25 feet. They mentioned where groundwater was encountered and it was sampled. And that sample indicated that the chemicals of concern were in excess of solubility limits for BTEX constituents. So basically, after this excavation, the groundwater impact persisted and did not attenuate. And then at some point, this site was closed out. The records are spotty, but it was reopened as part of a conditional no further action project that we do here, which is basically just to verify, you know, our closures. And obviously, when that happened, the chemicals of concern were above the site-specific, you know, target levels, and so it was reopened. So this was one of the first assessment reports that was completed at the site in 1995, and this was after the excavation was completed. And as you can see, some of the highest, I guess, overreadings were at 4 to 6 feet, from 4 to 6 feet to like 8 to 10 feet, and a couple significant ones at 14 to 16 feet. And here's a figure, and I apologize for the figure. Some of these older figures are not so good, but this is just a general layout of the site. And this is from that previous figure. The front of the road would be about right here where B9 is. But again, some of the highest chemicals of concern in the soil up here by the dispensers, 6 to 8 feet, and then one at about 14 to 16 feet here. And then still some significant hits over by the tank basin, 4 to 6 feet and 14 to 16 feet, but definitely the highest up by the dispensers. And then 3 monitoring wells were installed as part of this scope of work, and definitely the highest chemicals of concern in the groundwater were up by the dispensers in MW2, as you can see, and these wells were screened from 9 to 19 feet. So the next scope of work that was done was a rapid assessment in 1997, and this figure is showing the extent of the soil contamination that was delineated as part of this scope of work. And this just shows above the RBSL, so it doesn't show specific concentrations, but really it just showed kind of a limited extent off the corner of the building. And these are the 2 pump islands here, and then the former USTs would have been approximately over here. And there's another small area that they showed some more hits above the RBSL. And again, I apologize for this figure. I know it's hard to see, but this is one of the earliest potentiometric maps and one of the only ones we have. But I did want to show this because of it shows the what the groundwater flow looked like towards this monitoring well 8. And this is what the sample results showed for these monitoring wells. These are the most significant hits at the time in MW1, 2, and 6. all pretty much up here by the dispensers, except for MW6 that was closer to the tanks. So at this point in time, let's see, MW1 is screened from 9 to 19 feet right here. MW2 is screened from 8 to 18 feet. And MW6 is screened from 5 to 15. So it looks like this site was slotted for monitored natural attenuation, but the chemicals of concern did not decrease, it looks like. So that's why the site was reopened. And then at that point, when it was reopened, some recovery wells were installed in this area right about here, and I'll show you a map of that in a moment. Several AFER events were conducted, which is similar to what Dorothy was referring to as the MIMI events. However, the chemicals of concern persisted. So this site was chosen for HRSC. Recent groundwater data, which I didn't provide a figure for because we don't have a table, but recent groundwater data only showed hits, significant hits in the recovery wells in excess of solubility limits, as well as one offsite well, but no other groundwater hits. And one thing to mention is that the recovery wells are screened from 10 to 25 feet, so a little bit deeper than any of the existing monitoring wells, which is interesting. So after the AFERs, the next assessment that was done was the HRSC assessment, and this is just one figure that I pulled of the signals for the LAF and the MIHPT. And if you remember the previous soil COC map, it only had those two small areas. And what this shows is that the residual LNAPL signal is showing almost the entire property right there to the road and then back almost half the building. So there's quite a larger area of residual LNAPL than was previously thought. And then the dissolved plume is moving quite a bit further off site and really not in the direction of the groundwater flow. So I'm actually going to go forward a little bit to show you the map. So the potentiometric map previously was showing groundwater flow moving this way towards MW8, and it seems like the dissolved plume is actually moving more towards this way, towards MW11. I'll go back. And I'm not going to talk a lot about these logs just because I'm not an expert on this, but I did want to show some of these because they did show how deep in the source area that the residual LNAPL was going down. And some of our wells were screened properly in the source area, but some of them, a good bit of them weren't. So the first thing I guess to point out is that the residual LNAPL extent is larger and deeper than previously thought, like I said. So it's going down, past 20 feet, but obviously the majority of it is about 20 to 21 feet to 22 feet, but it goes down a little bit further than that. And these logs kind of show that there's, in the shallower zone up in the source area, there's, I guess, some smaller particle sizes, and this LNAPL looks like it's trapped right up in there. Still going down to about 20 feet. So, sorry, I'm going to go back to this. So, talking about these wells, MW1 is screened 9 to 19 feet. MW8 is screened 8 to 18 feet. And MW6 is screened 5 to 15. And the rest of them are about 5 to 15. So as you can see, most of them are not screened deep enough, and the recovery wells are screened 10 to 25, and they still show chemicals of concern you know, way above solubility limits, whereas most of the other wells are showing almost nothing, except for this offsite well MW11. So it seems like most of our wells are not screened properly for this site. So moving on to the MIHPT data and logs. The EC logs look a little bit different when you're moving towards the offsite, which is kind of interesting. And also the FID and the PIDs, again, show that the dissolved portion of the plume is quite a bit deeper than the wells are screened for some of these. And you're not seeing in some of the offsite logs that consolidated zone up at the top. So basically, what I wanted to demonstrate here is that with Larry's is that with the HRSC, we have better source area characterization. We identified the residual LNAPL. The excavation that was done originally clearly did not either go deep enough or extend enough to address all the residual LNAPL. Our wells were not properly screened. Offsite, the plume is going deeper as well. And it seems like, as John was saying before, you know, this site, it shows that perhaps the geology is influencing the plume movement more so than the groundwater flow. So we kind of, you know, discovered that, and possibly our recovery well placement could be better in that it could be, you know, placed more in the area of the residual LNAPL to recover some of that, if it is recoverable. Okay, so we learned a lot of things doing this project. We learned the limitations of the technology, and then just physical limitations. Dorothy was talking about some of that with, you know, can't really do this at active sites. I mean, there's structures, and you know, we ran into issues with trying to do this at, you know, sites that were drive-throughs and things like that. We ran into issues at sites that previously had not had issues with direct push technology, that had issues with this technology just because it's more sensitive. There's more downtime because there's more things that can go wrong, because there's just so much involved with it. It's a big time commitment from your project managers with the real-time data collection, and there's feedback that's needed in real time. So you spend a lot of time on the phone, or a lot of time reviewing the data in real time, a lot of time making decisions when the field work is actually being conducted. So that was definitely some of the lessons learned. But also we got to see how LNAPL and the dissolved plume actually behaves in the subsurface. It's almost always deeper than you think, almost always below the water table, almost always in multiple zones, both LNAPL and the dissolved. And one thing that we learned is you have to have proper communication in writing, and, you know, just communicating often and early. And I guess to wrap up, some of the benefits that we felt like, and some of the results and things that we felt were benefits, we felt like this will give us more accurate site conceptual models. We definitely gained a whole lot of knowledge of experience for our project managers and for our program in general. It will improve our assessments, even if it's just using traditional methods, but definitely using this technology. But if HRSC is not appropriate, it definitely gave us a better understanding of the need for more site-specific and, as John was saying, scale-appropriate data collection. And it's just given us a push for better assessment, soil assessment above and below the water table. And like I said, the need for more specific site-specific data collection as far as TPH, soil properties, discrete sampling, perhaps instead of having longer well screens, maybe paired wells for certain conditions. And we gained the information necessary to choose appropriate cleanup strategies at the sites where this was utilized and targeted cleanup approaches. And then we've gained some information for potential rate development in the future. Potentially we will be putting out a new contract to gather more information for potential rate development for more widespread use in the future of this technology at our sites. And that's what I got.
Great, Ashleigh. Really do appreciate that as well. So let me just go ahead and make myself the presenter. All right, and with that, again, we would like to invite the audience to go ahead and send in any questions that they would like for Ashleigh right now, and we will get to as many as we can, and then after that, we can open up for the more of a panel-like question session. So if we can start with the question, sorry, so many coming in. Bear with me 1 second. All right, is there an explanation for Ashleigh? Is there an explanation for the depth of LNAPL penetration at the case study site?
I don't know how to answer that exactly.
Okay.
Yeah, I mean, it's hard to say. I mean, we saw that at most of the sites. I don't know if John could answer that better.
Yeah, let me see if I can help out a little bit, Ashleigh. So again, I said LNAPL has a mind of its own. It also, the key is it has a thickness and a weight or a density behind that mindset, and the thickness of the LNAPL or the total head pressure of the LNAPL will drive it down during the initial release. And so if you think about a barrel of oil sitting on top of a sandy aquifer, that oil will go straight down a couple 100 feet if it's homogeneous sand. If you then saturate the aquifer, it'll go down until it reaches an equilibrium pressure with the water and then stabilize or at that depth. And if you have continuous release and you're constantly adding LNAPL thickness to the top of that release, then you're continuing to build the head pressure up, and so it'll go down. You kind of think of like a torpedo going down into the water. It'll go down and keep going until the resistant pressures makes it stop. Then you get into the heterogeneity of the soils, and it'll take off in different directions depending on the path of least resistance. And then the final thing that happens a lot is that we create an artificial pathway that's very permeable through the filter packs or the drilling operations or even the enhanced vacuum extraction oftentimes that we do on things, and we create an artificial pathway for it to follow. If it's got sufficient head pressure, it'll keep going down until the water makes it stop. So that's why we find a lot of LNAPL below the air-water interface, is it starts with just the mass of the LNAPL that drives it down. And And that's one of the misconceived notions that's out there, and it's an important one to grasp early.
Great, thanks so much. Question for Ashleigh. Prior to HRSC, how did South Carolina determine at what depth to screen monitoring wells?
Typically we go with a standard screen length of about 10 feet for our monitoring wells, but we just typically decide that through traditional field screening methods traditionally.
Great. Another question. Given the data, this is for Ashleigh, given the data, is the state considering revising all the sites with NFA?
Like, what do you mean revising, like reopening or?
Sorry, revisiting.
Oh, no, I don't necessarily think that we would do that, but we do have that CNFA project, as I mentioned, where we do verify our closures, and we do that periodically. So that is done periodically to make sure that with sites that still have monitoring wells, that our closure decisions have been appropriate.
Great. Appreciate that, Ashleigh. And now with about 15 minutes left, we're going to open it back up to just the to all of our speakers now. So let me sort through these. For Dorothy, how long to give a CAP to prove itself until you determine that it's ineffective? How do you determine a successful CAP?
Well, that's a great question. And we don't have a very specific answer for that. And John pointed that out, that, you know, in some cases, there's not a formal approach to doing this. Every site is different. The technologies being used at the site, you know, are designed to clean things up at different paces. All in all, something that I kind of had is more of a rule of thumb that, you know, if you're not seeing significant reductions at 3 years of operation, something's wrong. You need to modify that cap, switch gears, do something different. Now, unfortunately, that's not what we've done always at our sites. Some of these sites have gone on for a long time, beyond 3 years. So again, it varies, and we don't have a specific time frame for that. But I think really the sooner you start really questioning the viability of what's happening at the site, the better.
Great. Thank you, Dorothy. Appreciate that. This next question is going to be for John. What method would you suggest to properly scale the resolution for your data collection to the site or to the problem being investigated?
Good question. I mean, obviously, the geometry of the site has a lot to do with it. As we point out, sometimes you can't get where you need to go. We look at it is, do we essentially start with source areas, then we try to verify boundaries. And obviously verifying a boundary on an LNAPL is different than a dissolve phase, which may be more permeated through the soil structure. A tighter soil is going to have a closer spacing or resolution requirement than a more large grain permeable soil. So we work more from a lines of evidence perspective. In other words, do we start where we know we have probable sources based on historical data, then we verify boundaries, and then we go to what's the next line of evidence we want to do, prove PVI or not, prove dissolve phase migration or not. And so it's, and then you have to balance that against budget and time. So it's, again, it's like Dorothy says, every site's a little bit different, but using the lines of evidence approach, they come out roughly the same.
Great, thank you. Question for Dorothy. Does the effectiveness of multi-phase extraction events vary based on the duration of the event?
Wow, another great question. Ooh, see if I have a decent answer for that. Overall, what I've seen at a lot of the MIMI events is that unless it's just a really fresh gasoline release or got a lot of free product, you remove a lot of the volatiles in the first few hours of the event, and it tapers off pretty quickly. So there is a discussion on, should this be 8 hours? Should it be a 12 hours? Should it be a 24 hours? And I think you can try all those durations, but I think you really, before you go in the next quarter or the next event you do, you really ought to look at your data from the last event and see at what interval did you get the most reduction or the most extraction, and then use that data for your future events. Of course, you switch wells around. You know, you may do one set of wells this time, one set of wells the next time. So no specific answer on that, but I think the thing is that you need to look at the data that's collected from the event that you did and use the effectiveness of that to make decisions on the length of the next set of MIMI events.
All right, great. I think this is another one for you, Dorothy. Do you think that a mass/flux discharge metric should be used for decision making at less sites?
Some of our consultants do that. I'm not sure that they're all utilizing that tool or that metric. You know, all in all, any data I think that you can collect that's collected correctly and has been documented as useful in the decision making should be considered. And you just take the results of all of that data and make your decision, and not just hinge it on, am I above a number or am I below a number? Because we've seen where that's not necessarily the best answer for the site. You want to look at the whole holistic set of data and make, and if this is one of them that can be used, then it should be used.
Great. Question for John. Will collecting saturated soil samples help with evaluating the residual TPH mass?
Yes, I mean, that's exactly the purpose for doing that. So if you systematically, and what I mean by is basically using appropriate scale, how many samples do we want to take across a instance or an indication of LNAPL? So if we have a plume that's indicating it's, as Ashleigh showed, maybe a 5-foot plume, how many samples do you need across that to get a feel for the constituents and consistency and concentrations within that mass? And then using those numbers, so you might, for example, measure every foot coming through that plume. Take those numbers, and then you can come up with a total constituent mass, and then use that to go into the documents and determine whether you've got what your saturation concentrations are, and then, or percent saturations are, and then whether you've got the potential for mobility or recoverability. And generally, and what's the condition or stage of the degradation of that product. So.
Great. Another question. What are the main risks of concern in Alabama with residual contamination at UST sites?
Well, our process, you know, again, like I said, was a risk-based process, and of course, you're looking at risk to receptors. vapor intrusion, you got to check that box. Does the site have concentrations that are unacceptable for that pathway? Are there water wells in the area? We have a lot of rural areas in Alabama, a lot of public water supplies, but also a lot of private wells, as many states do. So you've got to look at, do we have a risk to private wells? Part of our risk-based approach is to have a kind of an attenuation zone, and we allow a point of exposure 500 feet from the source, and we want to try and meet drinking water standards at least 500 feet away from the source. So we have an attenuation zone that's there. So if there's, you know, residual LNAPL there and we can meet those numbers, then it's likely an opportunity to look at that and see whether or not we need to if we removed, can you remove that LNAPL? Have we removed it to the maximum extent practical? And keying in on what are the receptors at the site and just how much cleanup needs to be done. I don't know if that, does that answer that?
I think so. Got another one for you, Dorothy. How do you handle multiple releases that commingle? Is there a way to clean up one release separately from another?
Wow, that's another good one. I wish I had a full answer for that one, because that's one of the most challenging things you do. You know, all in all, as far as a cleanup strategy, you're looking at receptors, and you want to be sure a release at that site or any contamination that's present at that site does not pose a risk. You know, if you can clean up different plumes, if you can identify and separate them, we do that. But a lot of cases, it just becomes commingled. And we're fortunate to have a solvent trust fund, and most of our sites participate in the trust fund. And so we're able to clean up commingled plumes, whether it was something that was really old or something that was fresh. We go ahead and try and clean it up. But I think that's one of the most challenging things, is to try to figure out, you know, A, have we stopped the release? Where are the source areas? And how is that going to affect this plume of contamination we found, and to do it correctly?
Great. Another question for you, Dorothy. What additional analytical is being done and on what sample? How are samples being collected?
Okay, so that's some kind of what John was talking about. I know we're getting close to time here. It's good to go ahead while you're doing the high-res study to put in some new soil borings. And I believe that we're going back and testing for TPH again. We kind of dropped TPH when we did the Rebecca, and we went to just chemicals of concern. But we found that over time that perhaps we do need to go back and pick up some more TPH data, because it's giving you a different answer there. So we may do chemicals of concern and TPH in the soil, depending on what type of fuel release it was. So again, you're there getting data. Get the data you can while you're able to get it, and then use it in your decision making.
Great. So this might have to be our last question, either John or Dorothy. Have you seen that if there are dissolved impacts above MCLs in the monitoring wells, there is always a residual LNAPL found at that site?
I don't know that I could make that statement. John, you've probably seen more. You've seen more cases.
I'll just fall back on the ITRC thumb rule, which is if you've got a part per million in the well, then there's residual LNAPL in the vicinity. If you've got 100 milligrams per kilogram in the soil, there's LNAPL in the vicinity. Doesn't mean it's mobile or movable or recoverable, but it is providing sufficient electron exchange to create that dissolved phase problem.
Great. And it looks like we'll actually have time for one more question. What are the various states' responses to your recommendations to use HRSC to upgrade the CSM? And that's for all the speakers.
I didn't understand the question, Nick, and I don't know who
Sorry.
you're addressing it to.
Sorry, probably Dorothy and Ashleigh. What are the various states' responses to your recommendation? Oh, this is actually more towards you, John. What are the various states' responses to your recommendations to use HRSC when upgrading the CSM?
There's a whole spectrum of responses. You know, from we don't have a mechanism to do that, or we're waiting for the consultants to bring us a site, we'll be happy to look at it, to we're thinking about it. It's a number of different responses, but it really, I would say most of them boil down to it's different than the normal process that's going on. It's not a technical resistance. It's a how do we do this in our state? And it's more of an implementation, you know, sort of like Ashleigh outlined how they went about making the decision that they were going to do it. So it generally is not a technical objection. It's mostly how are we going to make this happen? And we need the consultants to bring us sites, and then we can look at it.
Great. I would like to take some time just to say thank you so much. And that is the time for our webinar. And again, thanking John, Dorothy, and Ashleigh for taking the time to present and stick around to answer questions on HRSC. So this webinar will be posted on the Newly Pick Underground Storage Tanks webpage, where you can find multiple resources, including archived UST inspector training webinars, as well as the Lust Corrective Action webinar series, and the complete archive of the Newly Pick publication Lust Line. Again, please take a moment to fill out the survey, which will be automatically opened the prompt after you close the GoToWebinar window. You should receive a certificate of attendance within the next 48 to 72 hours. I would like to thank everyone again for participating in today's webinar, and I hope that you join us for a future event. But until then, I hope everyone has a great day, and thank you so much.